So in this talk, we are gonna try and solve elliptic PDEs. So again, Poisson-like equations, and we are gonna try to do it fast and robustly. So I'm gonna start by introducing the hybrid high order or HHO discretization method. It's a discretization method that has a lot of let's say advantages compared to other older ones like standard finite elements or discontinuous Galerkin methods. And obviously, as you know, in our field, there is no such thing as a free lunch. So if we have a great discretization, it probably means that we are going to get a nasty linear solver. And obviously, this is the case. So in the second part, I'm going to talk about how we have managed to solve the arising system in with a multigrid algorithm of our design, and we're gonna end with numerical experiments and conclude with strengths and limitations of the method. So so as I said, we're working. We limit ourselves to scalar elliptic equations. So here the diffusion equation, and I'm gonna just enumerate quickly how the HHO method works. So it's a method that applies to a general polyhedral meshes, which is always a good thing if you want to, which offers a lot of flexibility to approximate complex regions of a geometry. It's working in a discontinuous setting, meaning that it's suitable to approximate non-smooth solution better than continuous finite elements, for instance. And unlike discontinuous Galerkin, it has much less degrees of freedom left in the system, thanks to hybridization that will allow for reduction of the number of degrees of freedom through a static condensation process. It handles a high order of approximation, and it benefits from a super convergence property, meaning that if the solution is smooth enough and if the degree of approximation is p, then the convergence, then the discretization will converge in h to the p plus 1. So that's nice. That's nice. That's actually better than other discretizations of the same kind, like a hybridized discontinuous Galerkin HDG, from which HHO is actually a subclass. So about the degrees of freedom, it's a hybrid method, meaning that that we have degrees of freedom located in the cells and on the faces, and each set of local degrees of freedom represent a local polynomial in cells and on faces. I'm going to talk about that later. So how do we exploit this hybridization? So as you can see in the global matrix, here it's order with the with the cell unknowns first, and you can see that the cell unknowns are only coupled to each other within the same element, or with the degrees of freedom located on the faces of that same element, meaning that element-wise, the cell degrees of freedom are decoupled, and we can exploit that because we can locally eliminate the cell unknown from the system. We just have to inverse a block diagonal matrix, and it gives rise to a Schur complement in which only the phase unknowns remain. So just to summarize the process, so we assemble the matrix, we proceed with the static condensation, leaving a Schur complement only with a phase unknown. So we solve that Schur complement for the phase unknowns, yielding polynomials on every face of the mesh. Here I'm saying face, but the schemes are in 2D, so it's H, but I'm using the 3D terminology. Then we reverse the static condensation, meaning solving the local blocks there to recover the cell unknowns, and we benefit from a higher order reconstruction operator. That if you have cell unknowns and phase unknowns of the same degrees, you can actually reconstruct a higher order polynomial, and that's where the higher order convergence of the method comes from. Obviously, the only costly part here is the solution of the Schur complement here, and we're gonna work on that with the design of a multigrid method. Now, multigrid, so as you know, a multigrid hinges on the definition of intergrid transfer operators, so prolongation and restriction. But in our method, we will use standard ingredients. Therefore, we will only define the prolongation, and the restriction will only be defined as the transpose of the prolongation, as it's often done. So in the condensed system, we are working with the phase unknowns only, meaning that that a discrete function of on the core skeleton is actually then a wireframe like this, and we want to extend that on the fine skeleton. And to do that, we are going to introduce an intermediary step of interior reconstruction. So from the faces there, we are going to reconstruct polynomials, local polynomials in the cells, and then we will be able to take the traces on the fine faces. So how do we reconstruct? We reconstruct a polynomial from the faces to the cell. Well, we are going to actually just simply reverse the static condensation, meaning that we are going to solve the local problem. So we just have the local blocks that we already reversed that we already solved for the static condensation. Well, we have to solve them back, and from the phase unknown resolve the small system for the cell unknowns. And now that we have a phase polynomial of degree k as well as as a cell polynomial of degree k, we can use the higher order reconstruction to actually build a better approximation, an approximation of degree k plus 1. And in the last step, well, now that we have degrees polynomials of a degree k plus 1 there on the mesh, we basically just have to take the traces on the fine faces to get back on the skeleton. So and this is done pretty straightforwardly. So if the fine face, here it's an edge, if the fine edge that we target is within a core cell, we can just take the trace simply and project the polynomial of degree k plus 1 onto the lower order polynomial space in order to retrieve our degree k. And secondly, if the fine edge is located at the interface between two coarse elements, we actually do the same thing, but we take the average value on the polynomials that we have on both sides. Okay, and for the rest of the multigrid components, they're going to be pretty standard. So the restriction is going to be the transpose of the prolongations. The coarse grid operators will come from the discretization. With a structured meshes. And what's important to us is the scalability of the methods. So we are going to raise the problem size. That's the number of degrees of freedom located on faces. So that's the system size. And that's the number of iterations of V cycles that we need to achieve a convergence, and we do the same test for multiple moderate orders of approximation. And obviously, if we want H independent convergence, we want flat curves, and that's what we have. So for basically every degrees, we have a flat curve, meaning that if we raise the problem size, the number of the convergence rate stays constant, or approximately constant. And we've done that for Cartesian meshes and triangular meshes in 2D, and Cartesian meshes and tetrahedral one for the unit cube, and it's working fine. Also, we've made some heterogeneous problems. So if we have the unit square and we divide it into 4 quadrants, we have a Kellogg problem, and we set the diffusion coefficient to be highly discontinuous across across subdomains boundaries, and we're going to raise the heterogeneity ratio up to 10 to the 8, and you can see that the convergence of the multigrid the convergence rate is actually almost oblivious of the heterogeneity ratio, which is good. And we do the same test, but this time a scalability test. So we fix the ratio, the heterogeneity ratio, and we raise the problem size, and it's still scalable. So for the quantitative analysis, we can say that our multigrid is fast, is scalable, and is robust to heterogeneous settings. And it also works the same way with about the same results in higher orders of approximations. The higher orders are natively managed by the multigrid at the cost of a block smoother. So you don't actually need to implement a P multigrid on top of the H1. HHO doesn't restrict the mesh structure. We can actually use polyhedral meshes, but there is no obvious coarsening strategy for polyhedral meshes, because our algorithm has one quite large limitation. That is that for the smoother to smooth well, we need the faces to also be coarsened between levels and not only elements. The algorithm also seems very sensitive to the mesh quality, which yields to actually not as good results if you're using very unstructured meshes in 3D. If the hierarchy of meshes are obtained by a tetrahedral refinement. Yeah, that's so for the continuity of this work, we're going to work on methods for unstructured meshes. And that's it for me. Thank you.
So Pierre, thanks very much for the nice talk. So we may have time for one quick question. Let us look whether there's anything coming up. So the organization says there has been no particular questions so far. So maybe I can ask a quick question. So this was for scalar equations. Do you expect any particular difficulty moving onward to systems like Stokes or Navier-Stokes?
Yes, I guess so. Because it won't yield elliptic systems, so I don't think a multigrid that straightforward will be applicable. But we haven't thought yet about more complex problems.